Okay, folks. Hey there. Hope you're enjoying your snow day. Here's a video to help you with the homework and also to explain things on L'Hopital's rule. That's how it's pronounced, no matter how it's spelled. And what L'Hopital's rule says is that if you're finding the limit of something, and as x approaches some value, and it's one function or another, if that limit is indeterminate, meaning it's 0 over 0, infinity over infinity, 0 over infinity, or infinity over 0, then the limit of what you're looking for is the same as the limit of the derivative of the top divided by the derivative of the bottom. All you have to do is take the derivative. And the beauty of L'Hopital's rule is you can take it 1, 2, 3, 4, as many times as you'd like. If you see a shortcut beforehand, like you see one thing is going to disappear, you can deal with that as well. Remember, this only works if the original limit is indeterminate. So even though you don't want to test it at first, you have to test it to see if it's indeterminate to begin with. So what I'm going to do in this video is I'm going to work each problem from the homework with all of the proper steps and terminology. Do you have to write down all the steps every time? Absolutely not, but I'm going to do it for this video right now so you can see them all. Okay, let's go on to the first problem. Okay, so here's the first problem. And what I need to do, even though I don't want to, is to fill in 0. So the limit of that function is equal to tangent of 0 over 0. And I always keep in mind, so cool 2. Tangent of 0 is 0. It's equals 0 over 0, which is indeterminate, which means I can take the derivative of the top and the bottom. Derivative of tangent is secant squared x over derivative of derivative of x is 1. I'm going to keep this here with me because the flip of secant is cosine. So the cosine of 0 is 1. So the secant of 0 is 1 over 1, which equals 1. That means if I took the original function, tangent x over x, and I graphed it, it would look something like, I'm making up the graph though, that, and would have a hole at 0 on the graph, and at a height of 1, 0, 1. It would have a hole. So let's take a look at the next one. I'm going to put down my so cool 2 to help me. I don't need an exclamation point there. And I have to test out the numbers in here first. This is equal to the sine of 0 over 0, which is equal to 0 over 0, which is indeterminate. Which means I'm going to find this problem by taking the limit of the derivative of each. The derivative of the sine of x is cosine of x over 1, which is equal to the cosine of 0 over 1, which is equal to 1 over 1, which is equal to 1. Which tells me the limit as x approaches 0 of sine of x over x is 1. Let's try the next one. The limit is x approaches 0 of 1 minus cosine of x over x squared. The hope is to not test it up, I'm going to test it anyway. So it's 1 minus cosine of 0 over 0 squared, which equals 1 minus 1 over 0, which equals 0 over 0, which once again is indeterminate. So let's use L'Hopital's rule. We'll take the derivative of the top and the derivative of the bottom. Derivative of 1 is nothing. Derivative of cosine of x is negative sine. So it's negative sine. So it's going to be sine of x over 2x. Now I'll fill in the 0. Sine of 0 over 2 times 0, which equals 0 over 0, which is still indeterminate. That means I can take the derivative again of the top and bottom, and hopefully I get an answer. Derivative of sine of x is cosine of x. Derivative of 2x is 2. Let's fill it in. Cosine of 0 over 2, which equals 1 over 2, and that's our limit. That means on the original function, as x approached 0, the original function approached 1/2. It was probably had a hole in the graph at that point. Okay, here's the next function. We're going to start by filling in the 0, and we get 0 squared over cosine of 3 times 0, which is 0, minus 1, which equals 0 over cosine of 0 is 1, which equals 0 over 0. Once again, it's not undefined. Ooh, close call. It is indeterminate, which means I can apply L'Hopital's rule. So this is equal to, I have to keep the word limit going, the limit as x approaches 0 of 2x over derivative of cosine of 3x is negative sine of 3x times 3. And the minus 1 goes away. If I fill in the 0, I get 2 times 0 over negative 3 sine of 0, which equals 0 or 0 again. Once again, it's indeterminate. Okay, let's try for a third time. See what happens. It equals the limit. I have to keep that word limit going. As x approaches 0 of 2 over negative 3. And the derivative of sine of 3x is cosine of 3x times 3, which equals 2 over negative 3 times 3, just rearranging, times the cosine of 0, which equals 2 over negative 3 times 1, which equals negative 2/9. Okay, let's try the next one. Cosines and sines are interesting ones because they flip back and forth, and you have to pay attention to the sign of what's going on. So here is number 8. Now this one's a little different. It says it's approaching from the positive direction. We'll see if that plays anything into effect later on. So when you see something like that, you can work out the problem normally and then see if it has an effect later on. If I put in 0, I get sine of 0 over 0 equals 0 over 0, which is indeterminate. So I can apply L'Hopital's rule. So it's equal to the limit as x approaches 0 from the positive side. Derivative of sine is cosine. X over 2x, which equals, if I fill it out in there, cosine of 0 over 2 times 0, which equals 1 over 0. Now, here's the key thing. It's really not the number 0 over here. It's the values close to 0 that are on the positive side. So what happens is this fraction really becomes a small number 1 over a really, really small number, like this. Made that one up though. And that number is positive. So because what happens is you have a really small positive number on the bottom, this value approaches infinity. And the reason they said approach 0 from the positive side, otherwise it's a negative value, and you have to head towards a negative value. So anytime you have a limit that heads to 1 over 0, it's going to head towards infinity from the plus side. Okay, let's try one more here. Let's fill in our 0. I don't really want to, but I'm going to do it anyway. It's 1 minus cosine of 0 over 0 plus 0, which equals 1 minus 1 over 0, which equals 0 over 0. Once again, it's indeterminate. So we can apply L'Hopital's rule, which tells us that the limit as x approaches 0 of that function is equal to the derivative of that function, which is sine of x over 1 plus 2x. We fill in the 0, and we get sine of 0 over 1 plus 2 times 0. Sine of 0 is 0 over 1, which equals 0. So the limit of this function is 0. Remember, if you get values of 0 over 1, that's an acceptable value. It equals 0. Let's try one more here. The limit as x approaches 0 from the positive side of ln of x over 1 of x. So I'm going to rewrite that because I don't like fractions if I don't have to have them. Limit as x approaches 0 from the positive side of ln of x over x to the negative 1. If I fill it in, I get ln of 0 over 0 to the negative 1, which happens to be indeterminate. So let's fill our answers on in. Let's take the derivative of it. Derivative top and the bottom, that is. Derivative of ln of x is 1 over x. And the derivative of x to the negative 1 is negative 1x to the negative 2. Once again, I'm going to get rid of fractions to make my life easier. Over negative 2. And I'd like to rearrange this if possible. So I can keep taking derivatives and fill them on in. I know this is equal to the limit as x approaches 0 from the positive side. Negative sign stays outside, that's this negative sign here. X over 2, x over 1. I just move them around. Positive side, I can cancel this. Get negative x. And so the limit as x approaches 0 is equal to the limit, is equal to, let's fill it on in, negative 0, which is 0. Okay, we're going to try this one now, but I know what's going to happen as time goes by, that x squared is going to disappear, but the e to the 3x is not going to disappear. But we're going to do all our steps like we need to do, which is we're going to fill things in. So we're going to fill in, this is e to the 3 times 0 is 0, over 0. What's anything to 0th power? 1 over 0. Oh, this one wasn't a L'Hopital, because that is not indeterminate form. That says that this number on the bottom is heading towards 0. So when that heads towards 0, the whole number heads towards infinity. It's a really big number on the bottom. Sorry, a really small number on the bottom means a really big number overall. So if you just L'Hopital this without filling in a number, you would not have got the right answer. Let's try another. Oh, lots of terms here. Do I want to fill in the 1? No, but I'm going to fill it in anyway. ln of 0 minus 1. Oop, I almost said ln of 0. It's ln of 1 minus 1 minus 1. Like I said, ln of 1 minus 1 plus 1 over 1 squared minus 2 plus 1. The ln of 1 is 0 over 1 minus 2 plus 1, which equals 0. 0, surprisingly, it's indeterminate, which means we can apply L'Hopital's rule, which means that the limit of the function above is equal to the limit of the derivative at the top, which is 1 over x minus 1 over 2x minus 2. I can fill the numbers in. I get 1 over 1 minus 1. I get 2 minus 2. And once again, I get 0 over 0. It's indeterminate again. Let's say we're doing it a third time, but I'm going to convert this before I begin to x to the negative 1. So I'm ready to work. And I get the limit as x approaches 1, negative x to the negative 2 over 2, which equals negative 1 to the negative 2 over 2, which equals negative 1/2. 1 to any power is still 1. That's why it works out like that. Okay, so this one is the limit, is x approaches 2, 3x plus 5 over cosine x. If I fill the numbers in, I get 6 plus 5 over cosine 2, which equals 11 over cosine 2, which is a number. I can leave it just like that. It is not indeterminate. I do not need to apply L'Hopital's rule. Okay, so on the next problem, I filled in the 2. I get tangent of 2 over 2 minus 2 equals tangent of 2 over 0. It doesn't matter to me what tangent of 2 is equal to. I know that this function is going to head towards infinity because the 0 on the bottom, an infinitely small number on the bottom, makes the number infinitely large. Okay, the next one is the limit as x approaches infinity of e to the x over x squared. I'll fill it on in, e to the infinity over infinity squared equals infinity over infinity, so it's still indeterminate. So if I fill in the derivatives of the top and the bottom, e to the x over 2x, I get e to the infinity over 2 times infinity, which is still infinity over infinity, it's still indeterminate. I can do the problem again. Let's use L'Hopital one more time. E to the x over 2, which equals e to the infinity over 2, which equals infinity over 2, which is infinity. The limit of that is infinite. Next problem, oh, it looks very similar. Well, we kind of know what's going to happen. If we fill in infinity, we get infinity over infinity. We're going to take the derivative of the top and the bottom, and the top one on this one is going to shrink down. That's still infinity over infinity. So we'll shrink it again. That's still infinity over infinity. One more time. Infinity of 6 over e to the x. That's 6 over infinity, and that heads towards 0. Well, why did the one before head to infinity? Well, what happened is the infinity part ended up on the top of the fraction, and the one that heads to 0, infinity, ends up on the bottom of the fraction. Okay, so these ones, if you want to do the shortcut, you can. I'm going to follow the rule all the way out. I'm going to fill in infinity. I'm going to get infinity plus 17 over infinity minus 11, which equals infinity over infinity, which is indeterminate. So I'm going to apply L'Hopital's rule. And I'm going to get 3 over 4, which equals 3/4. That's the limit of this function. Basically, you can look for the biggest exponent on the top and bottom as long as they match, and you could use them to determine what's going on. You could essentially eliminate everything else and just work with those two. So in the next problem, I already took the steps, and I found that the limit is -7 over 5. What I could have done is just, when you're heading towards infinity, only the biggest exponents matter. I could have grabbed those two, canceled out the x's, and realized it was -7 over 5. Let's try the next one. Oh, this one's so long. Well, I'm going to do all the steps, but I'm going to do it at once. Let's see if you can see that the answer is 1/4. Hold on. Okay, so here's the worked out problem for this one. And, oh no, I said I was going to get 1/4 because I looked at the biggest exponent in this one and the biggest exponent in that one and realized I was going to end up with 1/4. But I ended up with 6/24. Oh, which simplifies down into 1/4. So let's take a look at the next one. And it's heading towards infinity. We know that when we head towards infinity, only the biggest exponents matter. So I'm shortcutting it. I can get rid of those, and I can simplify by canceling those. And I end up with 3 over 7. That saves me doing L'Hopital's rule like 6 times. Now this one was not in your homework, but it's another type of L'Hopital problem that doesn't have a fraction. And I'm just going to show you it once. We may do it in review once or twice. It's supposedly not going to appear on the test anymore, but let's take a look at it. I'm going to set this equal to L. L equals the limit of that function. Now, you notice that I have something to an exponent. Well, what makes exponents go away? Well, I'm going to rewrite this over here. This side. I'm going to take the ln of both sides. Ln of L equals that. In which case, I can say the ln of L equals x times the limit. Oop. So I took the exponent and I brought it down. Now what I can do, this is x to the first, and like I said, we may not have to worry about this, but we're going to take a look at it anyway, equals the limit of the ln of x over x to the -1. Basically, I took this number, brought it to the bottom. So if I were to fill in 0 right now on this side, I would end up getting 0 over 1 over 0, which is 0 over infinity, which is indeterminate. So I'm going to apply L'Hopital's rule to this side of the equation. Once again, don't worry too much about this problem. I just want you to see it once. So you get it. It says that the ln of L is equal to the limit as x approaches 0. I'm going to take the derivative of the top and the bottom of 1 over -1x to the -2. So that says that the ln of L is equal to the limit Let's fill in the 0 of 1 over negative 1. Well, let's convert this. We'll do it like this. Over 0 to the negative 2. That negative 2 on the bottom is the same as a 2 on the top. And so the ln of L is equal to 0. So now I have to get L by itself. How do I get L by itself? I'll do e to both sides. They cancel. L equals e to the 0. L equals 1. We'll see more of this type in review when we get there. We're not going to write it right now, but we have our answers to our homework, and please go over it, and I'll see you tomorrow in class. Bye-bye.